Zaheen Ahmad. I am a PhD student here at the University of Alberta. I work under Michael Bowling and Levi Lellis. Um, did we start recording? Yeah, we started recording. So I guess I'll just get started. So today I'm presenting my work, Marginal Utility for Planning and Continuous and Large Discrete Action Spaces. This is based on a paper that my co-authors and I have submitted in 2020, and it got accepted there. My co-authors are Levi and Mike. One of the ultimate goals of artificial intelligence research is to develop AI agents that mimic general intelligence in sequential decision settings, such as games. This is relatively easy to do in smaller situations, such as games like tic-tac-toe, where the computers can enumerate all sequences of decisions in order to find the best action to take. But this becomes prohibitively harder in larger games like chess, which has around at most 35 actions on average per turn. And it's even more difficult in a game like curling, which has an infinite set of actions to choose from at each turn. Instead, what AI agents do is that they use sample-based search, which are a family of powerful algorithms that sample sequences in order to estimate outcomes in order to find good actions. One such algorithm is Monte Carlo tree search. Monte Carlo tree search iteratively builds a tree of states and actions in order to estimate the outcomes of actions. At each iteration of Monte Carlo tree search, we perform a number of steps. Shown here, illustrated on the right, is a partially built search tree where the circles represent states and the edges between circles represents the actions that lead to different states. In the first step of Monte Carlo tree search, we perform selection. We traverse down edges of the tree until we reach a leaf node. The selection during traversal is done using a selection policy, which determines which actions to sample. After we reach a leaf node, we expand the tree by including a child state from the leaf node. This child state is then evaluated by simulating until the end of the game is reached. The simulation is done using a rollout policy, which can be separate from the selection policy. Once we observe an outcome after reaching a terminating state, we use that value to update the values of all the nodes that we've traversed along the selection phase. The performance of Monte Carlo tree search is highly influenced by the set of initial candidate actions that it receives. Usually the candidate actions can exhaust the entire search space. Sometimes we limit the candidate actions that we search over using handcrafted actions that are built using domain knowledge. And recently, we've learned how we can sample actions from a learned policy instead in order to constrain the space we search over. In this work, we will focus on explicit candidate generation. That is, we want to train a model such that when it receives a game state, it outputs a set of candidate actions that we limit our search to. Is everyone with me so far? Okay. Thank you, Matt. So for example, let's say we have this two-dimensional continuous action space. The horizontal axis represents one parameter and the vertical axis represents another parameter. Let's ignore the values for now. But with each action parameter pair, we have a observed reward or a utility. And in this continuous space, we have this large space of parameter pairs to choose from. So how do we do that? How do we select which actions to search over? The candidate generator that we propose would be able to take a state like this and say, these are some parameter pairs you should check out during search. We restrict our investigation to the single decision domain in order to reduce the effects of value functions or rollouts on the performance of search. And the only thing that affects the performance of the search algorithm is the candidate actions themselves. In a single decision domain, we have a set of states, and each state has a set of actions. Uncertainty in action execution can be modeled using the execution model And this gives us a set of executed actions instead. Given a state and an executed action, a transition function determines the outcome of the action. Each outcome is associated with the real valued reward. The Q value of an action at a state is the expected reward achieved by that action under uncertainty in action execution. And the objective of the search algorithm is then to find the action at a state that achieves the highest Q value. Is everyone clear on the objective of our problem? Yeah, I'll take that as yes. So right now I will describe two different search algorithms that we can use in a couple different settings. The first search algorithm that we look at is UCB for discrete action settings. UCB tracks sampled averages of the Q values of the actions we sampled and the number of times each action is sampled. And at each iteration of UCB, we sample according to the UCB formula shown below. The first term in this formula is the sampled average of Q values that we've observed by sampling actions. The second term is an exploration bonus that adds a value to the sampled action or adds a value to the UCB value that increases with the number of times an action was not sampled and relative to the other actions. So this ensures that any action that was not sampled previously eventually will be sampled. And at each iteration, we select the action that has the highest UCB value. In continuous spaces, we can use UCB given a set of actions. However, this is not taking into account that we can leverage information based off of the uncertainty that we have from our execution model. Instead, we can use another method for estimating the values of the actions called kernel regression. So how does kernel regression work? Let's look at an example in this one-dimensional space. Here, the x-axis represents the space of actions that we can choose from, and the y-axis shows us the values of these actions. Let us say we have this set of observed actions and their rewards. And let's say our goal is to estimate the value of the action at x equals to 1. Using kernel regression, we use kernel methods to find a distance between all the sampled actions to weight the values of the other actions in order to predict the action that we are looking for. So for example, over here, we see that the kernel function that we used for this case places a number of weights represented by the green bars on the values of the other actions that have been sampled so far. And using these weights and the values, we can predict the value of the action at 1. So given a set of J actions and J observations, we can predict the value of any action A using the kernel regression estimate. The kernel function is a notion of distance between two actions, and W of A is the amount of information we have about a single action. Any questions so far? All right. We can modify the UCB formula from before to create kernel regression UCB for use in continuous settings with action stochasticity. We replace the sampled average using the kernel regression estimate, and the exploration bonus is replaced using the information bonus. That means actions that we don't have a lot of information about given the sampled data, we explore more, we will eventually explore at some point. So the cool thing about kernel regression UCB is that it actually helps us to refine the actions that we are searching over. Let's say we have that example from before where we have this 2D continuous action space and we have a set of generated actions. Kernel regression UCB will eventually lead to a set of samples that look like this, where the samples include new actions that we have tried based on stochastic execution. And we can select a final action based on these new added actions. So the search that we've done, the actions that we were given before can be refined to be a better set of actions. And we can end up finding actions that are better than that existed in our candidate set. Any questions? Okay, so search candidates matter. UCB requires sampling each action at least once, and this becomes intractable when we have a large number of actions at a state. And so candidate actions can limit the number of actions over which we need to search. And KRUCB is done in continuous settings where we have a potentially infinite choice of actions. And in order for KRUCB to work, we need to begin with a set of actions to search over. One recent method for limiting or constraining the search space is to use a learned policy to place probabilities over which actions we want to sample. Let's take a deeper look on how these policies work. Let's say we have a model trained to produce a policy at different states. So this model takes state. In this case, we have a state with 6 actions and 6 outcomes. The policy then places a probability on all the actions that we should sample. Over here shown, denoted as rho. We have a well-distributed policy over here, and it places relatively uniform probability on sampling each action. The policy is then used to augment the UCB formula so that the UCB value not only is determined by the exploration bonus we have, but there's also a factor introduced by the probability. So that means actions with a higher probability are more likely to be sampled. And given this probability factoring into the exploration, we do some sampling. And as we sample, we keep track of the total cumulative sample counts that we have so far. Once this search is run, we look at the counts of the samples, and we form a sampling distribution, which we call pi. This pi can be thought of as an improved policy from the one that we've output from the model. And the output policy is then changed so that it more closely resembles the sampling distribution. So we began with a more well-distributed set of probabilities, and now we place higher probability on the action that was sampled more. So next time we come across a state, we're more likely to sample that action over other actions. And in doing so, we limit how many actions we look at each state during search. But what is this policy actually optimizing? We have a set of sampled actions, A through M, and by mimicking the sampling distribution, what the policy is doing is trying to maximize the sum of the values of the actions. The problem with this is that this tries to ensure that all the sampled actions are high valued. This ignores the fact that these actions are going to eventually be used in search, which will have some improvement over these actions. We instead propose that we train a candidate generator by optimizing for the max of the actions at any state. This ensures that only at least one action need be high valued. However, there's another problem that comes when we're trying to do this. Let's look at it with an example. Suppose we have a set of actions and we see this set of rewards, 2, 3, 1, 6, 5, and 7. The max value over here is 7. And calculating the gradient of this vector, we see that we place a 1 only where the 7 was, and every other action has a gradient of 0. Now, this means that this is a harder landscape to optimize because of the very sparse gradients. We introduce a reformulation of the max objective. Let's say we have a set of M actions, and we've ordered these actions in order of increasing value. By doing so, we can write the max value as the sum of marginal utilities of the values of all the actions. The marginal utility of an action is the utility gained by that action over previous actions. If we retain only the positive differences by clipping all values at 0, then we can remove this need for ordering. But I'm going to ask everyone a question right here. What would happen if we tried to optimize this particular formulation right now? That's fine. So the thing is that given the way this equation is formulated, by trying to maximize this formula, what happens is that we can improve certain actions by decreasing the values of previous actions. And so what ends up happening is that by taking by optimizing this function, we end up just optimizing max. Instead, by placing a stop gradient in front of that max term, we prevent this phenomenon of reducing the values of previously generated actions in order to improve the later ones. Let's go back to that example we had, where we saw that the max objective produced a very sparse gradient vector. If we now look at the vector of marginal utilities, we'll see that there are more non-zero values in this vector. And taking the gradient of the marginal utilities now produces a gradient vector with denser gradients. Does anyone have any questions on anything so far? All right. To evaluate the performance of our proposed candidate generator, or our learning objective, we looked at experiments in 2 single decision domains. We looked at one continuous action domain with stochastic execution, and one domain with discrete actions and deterministic execution. For each domain, I will describe the setting, explain how we generate candidate actions, how we compute the gradients, and some experimental results. The first domain we look at is curling. Now, curling is a sport played between 2 teams of players on a sheet of ice. Teams take turns shooting rocks from one end of the ice to the other. Each game usually lasts 10 rounds, and the last shot of each round is the hammer shot. We will focus our investigation on the hammer shot. This leaves us a single decision domain where the actions are parameterized by a 2-dimensional action space. This is the same example as we've seen before. And we add stochasticity by adding noise to the values of the actions that we take by some learned execution model, or sorry, a calibrated execution model. And that introduces stochasticity into the execution of actions. After we play an action, we observe a reward. And the reward is the points scored by that action. If you're familiar with curling, you might think, isn't there also a turn that influences the actions? In our simulator, we model turn as a binary variable, and to restrict our analysis to the continuous parameters, we just set one turn to be constant for all actions, and so we only need to concentrate on the angles and the velocities. So we've trained a model to produce candidate actions. What that means is that at each state, the model takes in the state representation and outputs a set of M actions. These M actions are a pair of parameters of real values. The actions are then used to sample rewards in the search space in order to select the best action. But how do we train this model? Since the Q values are estimated using samples, we cannot directly compute a gradient with which we can update our model's parameters. Instead, we need to get a little bit more creative. So what do we do? Let's say we generate a set of M candidate actions. By sampling each action a number of times, we then observe a set of N observed actions and N observed rewards, where N is greater than M. Using kernel regression, we can actually make an estimate of all the generated actions, the values of all the generated actions using the observed sampled actions. We then use these Q values in our marginal utility formulation. And now we have a differentiable approximation of the marginal utilities of the actions in this space. The gradients for this value are then used, of this formulation is then used to update the model's parameters. In our experiments, we use a neural network as the model that we train. This neural network consisted of 2 convolutional layers, 2 feed-forward layers, and output a set of 32 actions for every state given. We sampled each action 4 times to train our model. We trained our model over 20,000 iterations of batches of 32 randomly generated hammer states. And then we test our model on 3,072 testing states. The first set of experiments that we look at tries to evaluate, sorry, I went ahead of myself. We will compare our model against a number of other models. We look at candidate generators trained using other objectives, such as the sum of the values of the actions. We also introduce diversity in the actions produced by sum by using an explicit diversity penalty, which penalizes the value of the sum by the proximity of the actions. We also train a model using max and softmax, which is a smooth version of max. We also compete against a policy. Now, this is a bit more tricky because we have a continuous space. So in order to train a policy, what we did was we discretized the space into a set of partitions. The policy then learns a probability over these partitions. During search, we sample a partition and sample a random point within that partition to get an action. And we use KR-UCB to refine the searches within partitions in order to refine the actions. We also compare against a set of handcrafted actions at each state. Now, the first set of experiments that we do look at or try to evaluate the quality of the actions produced by the different candidate generators. In this experiment, we only focus on marginal utility, the policy, and the handcrafted actions. The search that we used was UCB, and we performed UCB on subsets of generated actions. That is, for each generator, we looked at the first action and ran UCB, the first 2 actions and ran UCB, then 4, 18, 8, 16, and 32. After we ran UCB, we looked at the action that was selected and evaluated it 1,024 times to calculate an average reward. Then for all states, we measure the expected points achieved by search over all the testing states. The plot on the right plots the expected points achieved by search using the subset of actions generated by each generator. The blue line represents the expected points achieved by marginal utility over all subsets of actions. And we can see that this clearly outperforms the policy and the handcrafted generators in producing good actions. We only have 1 point for each of the bots or the handcrafted actions because they produce a different number of actions per state, and we looked at the average number of actions to plot their expected points. Any questions on these results? In our second set of experiments, we actually compare against all the other objectives. In this case, for all the test cases, we ran UCB and KR-UCB on the actions generated by all the explicit candidate generators. For UCB, we see that marginal utility, represented by the blue line, performs significantly better than all the other candidate generators. The max actually comes close, but still is outperformed by marginal utility. And when we're using KRUCB, we see that this difference in performance diminishes. That is because KRUCB has the habit of refining search to actions outside of the candidate set. And even though the actions produced by the other objectives may not be good overall, KRUCB can turn those starting points or starting actions into better ones. And so the performance of those actions increase with KRUCB. Any questions on these results? All right. We now look at the discrete domain in which we evaluate our candidate generator. To evaluate candidate generator in this domain, we design a location game, which is played on a grid of cells. Each cell has a utility, and actions constitute selecting cells to be a location, and locations get some utility based on which cells are nearby. And the objective is to select actions to maximize the utility achieved by our locations. Let's clarify this with an example. Let's say we have this grid, and there are two locations chosen, a blue location and a red location. The blue location gets a utility from all the cells that are closest to it in terms of Manhattan distance. That is the sum of the vertical and horizontal distances between cells. In this case, the blue location gets a utility from the top two rows of this grid. The red location gets utilities from the bottom row. Both of these locations split the utilities in the third row because the cells in the third row are all equidistant from both locations. Is the location game clear to everyone? For our experiments, we looked at 10 by 10 grids for each state. And for each state, cells have a utility drawn from some random distribution, and they are all normalized so that the sum of the utilities are 1. For our actions, the agent that we train chooses 3 locations to be in action. Based on the combinatorics, then, at each state, the agent has a set of 1 million actions to choose from. The opponent chooses 2 locations that are determined by the utilities of the cells. The opponent will always choose the 2 locations with the highest utilities. In the discrete domain, for each state, the model outputs a set of policies. And from each policy that we output, we sample 1 action. Now, this may seem a little confusing at first, but what's going on? So the policies tend to become deterministic over time. And so as they focus their probability masses on a single action, the model is then similar to the previous setting where they end up just outputting a set of actions instead. So each policy then codes for a separate action. Again, we have to find a way to calculate the gradients because we are looking at sampled observations and sampled rewards. So let's say we generate a set of M policies and we sample an action from each policy. So we have M sampled actions. Now, using the log derivative trick, we can actually represent partial derivatives of the actions as a sum of the product of the marginal utilities with their log probabilities. This allows us to compute the gradients in the discrete space using sampled observations. For our experiments, we train a neural network to output policies. The neural network constitutes of 2 convolutional layers and a single feed-forward layer that outputs a set of 8 policies. From each policy, we sample 1 action. We train over 75,000 iterations of a batch size of 32 random states each iteration, and we test on 510 testing states. We compare against max and softmax learning objectives. Each of these objectives train a model to produce 8 policies from which we sample 1 action. We also compare against reinforce. Reinforce trains a single policy from which we sample 8 actions. So for each test state, we generate a set of actions from the policies, and we select the action with the highest utility. Since there's no stochasticity and transitions are deterministic, we don't need to perform search, and we can directly select the best action. We then average over all states to calculate the expected utilities of the actions generated by each of the models. The figure on the right plots the expected utilities of all the training objectives that we look at. From here, we see that it is clear that marginal utility and the max both outperform reinforce. Now, in this case, marginal utility does not significantly outperform max, because the optimization landscape in this case may be a little easier to optimize, and so max is sufficient enough to do the job for training a candidate generator. In conclusion, I talk about how candidate generation is critical to the success of sample-based planning. I also discuss how good policies do not necessarily make for good candidate generators, and show that max is an alternative learning objective that is more aligned with search. Marginal utility is a reformulation of max with better gradients that ultimately lead to better candidates for search. Thank you. I guess I can leave the thing open to questions now. Is that a question, Matt?
Yeah, it's a question. Thanks for the talk, really good. So I had a question about sort of the distinction that you would grab, or that you'd pull from these results in terms of between max and marginal utility, which is basically boils down to when would you recommend using max and when would you recommend using marginal utility?
I would say always go for marginal utility.
Okay.
Because there is, the only difference is that marginal utility can lead to better action, while training them is really the same. So it's not any more difficult to train a model using marginal utilities. So why not? At worst, it can do as best as max.
Gotcha. Okay. All right. Yeah. Fair answer. Fair answer.
Hi, Zaheen. Thanks for the talk. It was really good.
Thank you.
So you've run this in some kind of small single shot domains. Have you tried this at all in a bigger, like multiple stage kind of setup?
Good question. We are actually working on extensions to this, to the sequential setting domain. And that is the current work that I am looking at right now with help from another grad student.
Nice, thanks.
Is that it? I mean, free to take more questions.
Yeah, I have a question.
Yeah.
Have you ever looked at what effect it has if you don't, like, what if we don't know the execution uncertainty of the environment, and we have to use like an arbitrary kernel for kernel regression? Have you looked into that at all?
Yeah. So when we're performing search First of all, we usually have knowledge of the model's dynamics. So that's when we typically use search algorithms. But I have looked at the performance of marginal utility using a separate execution model. And we found that marginal utility still performs really well with some other execution model. In particular, I used the Gaussian kernel instead of the execution model, and that performed well too.
Cool, thanks.
Actually, to follow up on that, have you looked at other ways of doing regression? Like, I mean, deep learning, right? Or you can combine deep learning with kernel regression. Have you thought about anything like that? Or would that be useful at all?
No, I have actually not thought about learning a regression model, but I feel like that may complicate training. Now we have two different things to learn over, or it may actually help training by, you know, oh, here's another auxiliary task that improves the performance of the model. I don't know. That is something definitely that is worth investigating, but I have not done so yet.
Anyone else have any other questions for Zaheen? Must have done too good a job explaining everything, Zaheen.
Or I did not explain enough. But yes, if anyone has any other questions at any time, they can always reach me on my email or something. I'm always willing to talk.
Great. Well, thank you very much. We can end a little bit early today, and maybe we can enjoy some of the sunshine outside. Thank you again, Zaheen. And we will see everybody next week, same time, same place. Okay, have a great weekend, everyone. Bye-bye.